In this section, we'll compare the slopes of isothermal and adiabatic curves. And if we start with isothermal curves, so we can say for isothermal process, we know we can write PV is a constant. If we differentiate this expression, we'll get P dV plus V dP is equal to 0. And from this expression, we can find out the value of dP by dV, that will give us minus P by V. So this dP by dV can be written as slope of isothermal indicator diagram. This is the slope of isothermal ID. That means tan theta of isothermal indicator diagram is minus P by V. Similarly, we can also find out the slope of adiabatic ID. So we can write for adiabatic process, we use P V2 per gamma is a constant. So if we differentiate this expression, this will give us dP V2 per gamma plus gamma V gamma minus 1 dV into P is equal to 0. Now in this situation, here V2 per gamma can be cancelled. So this will give us the value of dP by dV, which is equal to minus gamma P by V. This we can write as slope of adiabatic indicator diagram. Now if we compare these two slopes for the curves, so we can write dP by dV of adiabatic curve can be written as gamma times dP by dV of isothermal curve. Practically, we are talking about the magnitude. Even if we use the absolute values, we can state this gamma times the slope of isothermal curve. That means as adiabatic curve has more slope compared to isothermal curve. So we can say in graph, this implies in graph adiabatic curve is always steeper than isothermal curve. Reason is always we know that the ratio of specific heat gamma will be more than 1. As gamma is more than 1, the slope of adiabatic curve is more. That means always the adiabatic curve will be steeper than isothermal curve. So here if we plot the isothermal as well as the adiabatic curve on an indicator diagram, we can see the difference. From the given initial state one, if we plot an isothermal curve, it will be symmetric with respect to pressure as well as volume axis, because this curve is the rectangular hyperbola which is used for isothermal process. If we talk about an adiabatic process starting from the same state and going up to the same pressure, say it is P1, this P2, then we can state if initial volume is V1 and in case of isothermal process final volume is V2, then from the initial state, same initial state, if the gas undergoes an adiabatic process, this curve will be steeper. So it will reach to another position which is say 2 dash. So this will be for an adiabatic process because the slope is gamma times that of the isothermal curve. Now, if the process is carried out for a monoatomic and a diatomic process, we know that gamma for monoatomic gas is 1.67 and gamma for a diatomic gas is 1.4. Then still the further difference can be seen. Say this 2 double prime. In this situation, this is the curve which is plotted for gamma equals to 1.67. And this is the curve which is plotted for gamma equals to 1.4. Here we can see that corresponding to the same pressure variation, monoatomic gas, if it is expanded, the work done will be least because it will expand by the less amount as the curve slope is higher compared to the case if the gas is diatomic, and if the same gas is undergoing an isothermal process, the slope will be less and the work done will be relatively more. You can see the area is increasing. So always be careful about the analysis of indicator diagram. Same diagram can also be plotted for same variation in volume, like if from the initial state an isothermal curve is plotted to an expansion volume V2 for a gas which is starting from V1, and from the same initial state, if the gas is undergoing an adiabatic process, the curve is steeper. For the same volume, you can say the total amount of area under the curve will be less. If it is done for a monoatomic gas, it is further steeper. So you can say area will be further less. So you can say there's a situation for a diatomic gas and there's a situation for a monoatomic gas.